All right, Unit 3, Video Essay 3. Let's start with the composition of blood. So blood is composed of plasma, and then we have our formed element here. So plasma is 55% of the blood volume, it's 92% water, and the plasma is going to contain proteins called colloids. And the main ones are albumin, globulin, and then fibrinogen. So our albumin is going to be our most abundant protein in the plasma. It is going to establish our blood colloid osmotic pressure. Our globulin carries antibodies, and then the fibrinogen is going to be an important clotting factor in hemostasis. So our formed element consists of red blood cells, white blood cells, and platelets. Our hematocrit is going to be the percentage of red blood cells that we're going to have there. And this is the other 45% of our blood volume is our formed element. So basically, we produce about 2 million red blood cells each second. So if we're producing that many, a lot must also be dying. So we need a system to get rid of that. So this is what this system looks like. So what's going to happen is we have these erythrocytes here. Once they reach about 120 days old, they get old and damaged, and then there's these macrophages that do phagocytosis, and they eat these old red blood cells. And then inside the macrophage, we have our lysosome, which is going to break down our globulin components of hemoglobin into amino acids. And then the heme component is going to be broken down into heme groups and iron ions. The heme groups are then going to become biliverdin, and then biliverdin is going to be turned into bilirubin, which is going to be sent to the liver. And then the iron ions are going to be shipped on transferrin, put into ferritin, back into the liver. So over here we have our free bilirubin in the blood. It's going to enter the liver, where it becomes conjugated. The liver likes to add glucuronic acid onto the free bilirubin, and this is going to make conjugated bilirubin. And it's going to be secreted into the intestines within bile, and the bacteria in the intestines love sugar, so they eat this glucuronic acid, and we get urobilinogen. So we have a few pathways here from urobilinogen. We can go into the bloodstream for a second round through the liver. We can go in the bloodstream down into the kidney, where we're going to be converted into urobilin and excreted as urine. And urobilin has its yellow color. And then, or we could travel down the intestine further and be converted into stercobilin and then pooped out, and that would be brown, right? All right, so now we've got hemostasis. So this is stopping bleeding. So in hemostasis, we have our vascular spasm. So let's say that we cut a vein or an artery. What's going to happen is we're going to send the pain signal through an afferent neuron to the control center, which is going to send an efferent neuron and cause smooth muscle contraction around that blood vessel, which is going to help stop some of that bleeding. So this is a reflex, but it doesn't last very long though, but it is the first step of hemostasis. And then what's going to happen is we have in the blood something called platelets, and platelets come from megakaryocytes. And these platelets are going to help stop our bleeding. So what happens is the endothelium of blood vessels always is secreting what's called VWF. And then VWF is going to bind to the collagen of an open wound site. These platelets want to bind to this VWF when it's bound to this collagen. So the platelets are going to bind to VWF, and then they're going to turn into their active form. Now in their active form, platelets have two different granules, alpha and dense. And the alpha granule is going to secrete platelet-derived growth factor, which is going to help with wound healing. And we're going to also excrete more VWF to help assist with the binding of more platelets to the open wound site. And then it's going to secrete fibrinogen, which is going to bind our platelets together to help us get a bigger network. And as each of these platelets activate, they in turn activate more. So we have a big positive feedback cycle here. And then our dense granules are going to secrete ADP, which is going to activate these new platelets here. And then in our clotting cascade, this happens simultaneously as our platelet plug is formed. So factor 12 makes surface contact with the wound site. It becomes an enzyme called 12A. 12A takes 11 and turns it into 11A, and then 9 is turned into 9A, and then we have 10 that's turned into 10A, and then this is where we're trying to get. So this, what I just laid out, was the intrinsic pathway, and this is going to be the common pathway. So 10A, this is the point of what we're trying to do here. We're trying to turn prothrombin into thrombin, which is going to turn fibrinogen into fibrin, which is going to cause our stable fibrin clot. And then the extrinsic pathways, we have tissue damage, and those tissues have tissue factor, or factor 3 on them. And when that tissue is damaged, we get destroyed phospholipids, and we get this factor 3, which is going to combine with factor 7 to make factor 7A, which is going to turn factor 10 into factor 10A, and then we're going to go down the common pathway there. And then the way that our clots are dissolved, because we have to dissolve these clots, right? So TPA and urokinase are going to act on plasminogen, which is going to turn into plasmin, which is going to cut fibrin into fibrin degradation products. All right, so this was a little bit of a shorter one today, but covered all the questions, so I appreciate it. Thanks for watching.